Hey, and welcome to your very last lesson for Chem 131. Congratulations. We're going to be wrapping things up today by talking about standard potentials and cell voltages in voltaic cells and also some other applications. So if you recall, last lesson, I introduced this voltaic cell composed of zinc, which is undergoing oxidation in the anode, and copper ions, which are undergoing reduction on the cathode side of this electrochemical cell. So a few terms I want to introduce right now, and just also a sort of general overview of what's happening. This cell is creating a spontaneous flow of electrons, and we can call this the electrical current. This is what can really do the work, such as turning on a light. I'm going to focus more, though, today on voltage, and this is a measure of the differences in potential energy between the cathode and the anode. And it's really what causes electrons to move. These two terms are easy to kind of confuse, and I often think of the analogy of a river. The current is how much water is moving through the river, and the voltage is like how steep the river is, comparing a flat river to a mountain stream. So yeah, the nature of the reaction that's happening, in this case, zinc plus copper ions yields zinc ions and copper metal. That's what's really affecting that cell voltage. So we can really easily measure this standard cell voltage, which we symbolize with a capital E with the degree symbol. As long as we meet some kind of defined conditions, which aren't terribly important, we can attach a voltmeter to this system and measure the electrons moving from the anode side to the cathode side. And if we want, we can even put a little LED lamp or something on there. So for this particular cell, using zinc and copper, the cell voltage is 1.1 volts. A positive value for that cell voltage indicates that this reaction is spontaneous in the way that we've defined it, in the direction that we've defined it. We can further kind of think about this cell voltage as being a function of the standard reduction voltage and the standard oxidation voltage. So basically, just sort of the energy levels almost of the two half reactions. Now, we can't measure those half reactions in isolation because we can't do half reactions in isolation. There always needs to be oxidation occurring with reduction. But what we've done over the years as chemists is that we've defined all of these half reactions in reference to what's called the standard hydrogen electrodes voltage, which we've defined as 0 as kind of a baseline. So really we just took one redox half reaction, and that's the hydrogen reaction, which we'll see later. And we're kind of comparing everything else to that one. Now, when we look at this table, we're usually looking at reduction voltages as opposed to oxidation. So let's see kind of what that looks like. So for example, for those copper ions that we have in this example cell that we've been looking at, when copper ions accept 2 electrons to form copper metal, the standard reduction voltage there is 0.34 volts. Now, I know you can't read this chart probably unless you're on a really big screen, but this is some standard data. I've put it up on Brightspace as well that shows lots and lots of reductions. So you can see on this chart that, yeah, all these reactions are written as something plus electrons, or maybe there's 2 reactants, yields something else. And there's a whole bunch of voltages listed for these reductions. So let's think about sort of how to read these reactions. If we're reading it from left to right as they're written, they are reductions. We could consider these reactions and kind of read them from right to left. Then they'd be oxidations. So let's think about what these standard reduction voltages really mean. These more positive numbers on the bottom right, they want to undergo reduction. They are prone to going through reduction, and they don't want to oxidize. So for example, one that's listed here is fluorine, difluorine, accepting 2 electrons and forming the fluoride ion. That means that, yeah, this reaction really wants to happen as written. Fluoride doesn't spontaneously go to the left to form difluorine gas. That would be a problem because we've all got fluoride in our toothpaste, and if it were spontaneously turning into fluorine gas, we'd all be dead. So, not a good thing. A couple other terms here. The bigger this standard reduction voltage, the stronger this thing is as an oxidizing agent. So fluorine gas is an incredibly potent oxidizing agent, which means that it makes other things oxidize. What about the really negative numbers at the top here, on the top right? So when our standard reduction voltage is more negative, these are species, lithium ions, potassium ions, sodium ions, that don't want to reduce. So they are not going to very easily go from being sodium ions to sodium metal. Again, the sodium ions in our table salt that we put in our French fries, not going to very easily just turn into sodium metal, which again would be very dangerous for us if it did. So these species want to oxidize. And so for that oxidation, we're looking at it in the reverse direction. Sodium metal, if you've ever seen sodium metal react with water or oxygen in the air, it explodes. And that reaction to form sodium ions going right to left happens very readily. So we can call these things strong reducing agents because they want to give those electrons to whatever else is around and make that other species reduce. So yeah, the higher up on this list we are, the stronger the product is as a reducing agent. So let's look at a couple of things we've talked about. I mentioned the hydrogen reaction. This reaction is just hydrogen ions accepting electrons to form hydrogen gas. That's the reduction that we've defined as kind of the baseline. We just call that 0. And then we were looking at the oxidation of zinc, and we were looking at the reduction of copper. So the copper ions are lower down on this list. They have a more positive standard reduction voltage, meaning that when we couple copper and zinc together, the copper is going to undergo reduction while the zinc is going to undergo oxidation. We're going to go right to left. Zinc metal will oxidize and give off those electrons to form zinc ions. Those electrons are then getting picked up by the copper. So let's practice calculating that standard cell voltage. That was kind of our goal here that I mentioned. If we know the standard voltages of our two half reactions, the reduction and the oxidation, we actually just have to add them together. Pretty straightforward. So yeah, in that cell, zinc was oxidizing and copper ions were reducing, right? So when I looked at that table, they're all written as reductions. So I need to kind of consider how to use that information. The second reaction here, the copper accepting electrons, that's what's happening. But for the zinc, the reaction's going the other way. Zinc is oxidizing to form zinc ions. So I actually want to write this reaction the other way. And when I do, I'm going to flip the sign on that standard voltage. But once I do, I can just add together 0.339 volts. That's the standard reduction voltage for the reduction of copper. And then plus 0.762 volts for the oxidation, the standard oxidation voltage of zinc. And that gives me a voltage of 1.1, which, if you recall, that's what my voltmeter said when I had that on the diagram. So a positive value here indicates that, yeah, this reaction is spontaneous. So let's practice utilizing this in kind of what you might see in a homework problem or something like that. Here's a question. Which of these reactions, or will either of these reactions happen spontaneously? And let's take a minute to kind of break them down. So in the first reaction, I've got nickel metal plus zinc ions yields nickel ions plus zinc. So our nickel is undergoing oxidation, and our zinc is undergoing reduction. So I'll just do an R and an O. I usually write RED and OX, but because I'm using my mouse, my trackpad, let's not do that. So yeah, that's what's going on in this first reaction. And the second reaction looks very similar, but the second reactant here is the copper ions. So again, we're seeing, the question is, can this reaction happen? Can this nickel oxidize in the presence of copper ions, which for this to happen would have to reduce? So we kind of understand what the reactions are doing now. How to answer this question, we can keep in mind that if that calculated cell voltage is positive, the reaction will be spontaneous. So we could calculate that cell voltage. Let's also kind of think holistically about this question and think about other ways we can phrase the question. Since we in the first reaction on the left, we said, well, nickel's oxidizing, zinc is reducing. So for that to happen, the electrons from nickel must be accepted by the zinc ions. So will that happen? Will the potential energy lower if that does happen? Will the zinc ions accept electrons from that oxidizing nickel? And then can kind of ask some similar questions with the second reaction. Will electrons flow from nickel to copper ions? Does that kind of lower the energy? Will copper ions reduce or accept electrons to oxidize that nickel? And maybe another way to think about this is between the zinc ions and the copper ions, both of the electron acceptors, which is a better electron acceptor or a better oxidizing agent? Which is more prone to undergoing reduction? So maybe that chart we were looking at could be helpful here. So I've got this color-coded. Black is the reaction involving nickel. So they're all written as reductions again, but nickel accepting 2 electrons to form nickel metal. And copper's way down here. And if you recall, the lower down it is, the more positive that standard reduction voltage, the better it is at undergoing reduction, the stronger it is an oxidizing agent. So that's a pretty good clue right there. Copper's the stronger oxidizing agent. It's more prone to accepting those electrons. So let's approach it mathematically now as well. So when I go to that table and I look up these standard reduction voltages, I've got the nickel reduction at negative 0.25, the zinc reduction at negative 0.763. So the reduction of zinc is what's written in the reaction, but for the nickel's undergoing oxidation, so I have to flip the sign on that voltage. But then I just add them together, and indeed my cell voltage overall is negative, meaning that this reaction is non-spontaneous. On the other hand, for the copper, if we go through that same process here, in this case, my overall cell voltage is 0.337 plus 0.25 to give me a positive value. So experimentation also backs up what that calculation is telling us. If we put a piece of nickel metal just in a copper sulfate solution, that reaction will be spontaneous. So this is that direct electron transfer as opposed to indirect, where we would have the half cells and the wires and whatnot. But yeah, direct electron transfer is really easy to kind of test. We just stick this piece of nickel metal into the copper sulfate solution. And what we would see pretty quickly is, I think you guys can see this copper plating out on the piece of zinc. So that electrode gaining mass by those atoms of copper plating out on it. And the blue color of the copper solution would be replaced by a green color, which is indicative of the nickel ions.